Hello everyone, I'm Prantar Ghosh from Dartmouth College, and I'm going to talk about graph coloring via degeneracy in streaming and other space-conscious models. This is a joint work with Suman, Bera and my advisor Amit Chakrabarti, and also thanks to them for helping me make these slides. In this work, we study the problem of vertex coloring. Here we need to assign colors to the vertices of a graph so that no two adjacent vertices get the same color. This is called a proper coloring of the graph. And for example, in the graph shown here, we can get a proper coloring by coloring in this way. In order to obtain such a coloring, our goal would be to use as few colors as possible. So the coloring shown here is proper, but it's not optimal. So now if we color it in this way, we get an actual optimal coloring. And this minimum number of colors required to color a graph G is called its chromatic number, denoted by chi of G. Graph coloring is an extensively studied problem in computer science, and it has several applications in various problems like scheduling, symmetry breaking, uh, register allocation, just to name a few. However, it's incredibly hard to compute an optimal proper coloring or this number chi of G, and it is NP hard to even get a approximation factor better than N. Given this hardness, a natural approach is to color the graph using a more tractable parameter like the max degree of a graph, which is denoted by delta G. It is known that every graph is delta plus 1 colorable, and a very simple greedy algorithm achieves this coloring. So in the graph as I have shown here, its maximum degree is 3, and so we can color it with four colors in the following way. We just assign each vertex the first available color that's not assigned to any of its neighbors. So if we color it using any arbitrary ordering and following this algorithm, we would color it with 4 colors. So in general, graph with maximum degree delta will be colored with delta plus 1 colors. Now this greedy algorithm takes space and time linear in the number of edges. However, this is infeasible for the big graphs that we see in the real world with billions of edges. And so a natural question is whether we can get a delta plus 1 coloring algorithm with sublinear space and time. This question was explored by Asadi Chen and Khanna, and in fact their work won the best paper award at SODA last year. There is also another drawback of this algorithm, that it's inherently sequential, which makes it infeasible to be implemented in the parallel or distributed settings. So a long line of research explores whether an efficient delta plus 1 coloring can be achieved in such settings. In this work, we study a different parameter called the degeneracy of a graph, denoted by kappa of G. Degeneracy is the minimum case such that every subgraph of a graph has a vertex of degree at most k. So this parameter degeneracy is actually a good measure of the sparsity of a graph. For example, the degeneracy of a forest is 1 because every subforest has a 1 degree vertex. Again, the degeneracy of a planar graph is 5 because every subgraph of a planar graph has a vertex that of degree at most 5. And for the densest graph, that is the complete graph, the degeneracy can be seen to be n minus 1, and in this case it is equal to the max degree delta. Now, by definition, kappa is always at most delta, and in fact it can be arbitrarily smaller, as is shown by the example of a star graph where the degeneracy is 1 but the maximum degree is n minus 1. So it is also known that graph is kappa plus 1 colorable, analogous to delta plus 1, and a very simple greedy algorithm analogous to the one that I showed in the last slide achieves this coloring. This coloring is different from the earlier one in the sense that it follows a particular ordering of the vertices, which is called the degeneracy ordering, and then colors it greedily as before. So in this graph, if we color it using a certain ordering of the vertices like this, and assign a vertex the first available color, then we would color it with kappa plus 1 colors, and we can see that for this graph, this time we colored it with only 3 colors instead of 4. As kappa is smaller than delta, kappa plus 1 coloring is always more efficient than delta plus 1 coloring. But again, this algorithm is sequential and it takes linear space and time, so it would be infeasible in the sublinear and distributed models that we study. It should be noted that the degeneracy is closely related to another parameter called arboricity of the graph, and in fact, kappa lies between alpha and 2 alpha. It is known that every graph is 2 alpha colorable, and this kind of coloring is particularly helpful for sparse graphs. And therefore, multiple recent works have studied arboricity-based coloring in distributed as well as in the dynamic settings. In this work, we would focus on getting proper colorings using approximately kappa many colors. Now, for some concrete numbers, we look at some real-world big graphs, which shows that in the real world, social networks, the web graphs, or the biological networks have degeneracy significantly smaller than the max degree. Therefore, if we color it using approximately kappa many colors, it would be more color efficient than an algorithm that colors it with delta plus 1 colors. Now, let me define the models that we study here. So the first one is the data streaming model, where the graph is built by edge insertions and deletions that arrive in a sequence. We don't have enough memory to store the entire graph, and so we have to store only sublinear, we have to store information sublinear in the number of edges, and then try to answer questions about the graph with this limited information. The next model we study is the graph query model, where we have oracle access to a graph, and we can make queries such as we can ask if two particular vertices share an edge or not, and the oracle checks it and replies the answer. And for example, in this graph, if we also ask if there's an edge between B and D, the oracle would check and reply no. And we can also make neighbor queries which asks for some number I, which is the ith neighbor of a vertex V. Our goal would be to make as few queries as possible, and definitely the number of queries should be sublinear in the number of edges, and making these many queries, we would want to solve the underlying problem. We also study a number of distributed computing models, namely the MPC, congested click, and the local models of computation. I won't go into the exact definitions of these individual models, but the main common setting that they have is that the graph edges are distributed across the processors, which communicate in synchronous rounds, and our goal is to optimize the number of rounds, such subject to the various communication and space restrictions that these individual models have. This brings me to our upper bound results. We give the algorithms for degeneracy-based colorings, which use kappa times 1 plus small o of 1 colors in each of these models. And if we see the complexity parameters like space, time, number of queries, or number of rounds remains the same or even better than what prior work has achieved for delta plus 1 colorings in the corresponding models. So our algorithms are color efficient for particularly the bounded degeneracy graphs, which is a broader class than bounded degree graphs, for which delta plus 1 colorings are good. And it should be also noted that our algorithms, while reducing the number of colors, are also simple to implement and analyze than the corresponding delta plus 1 coloring algorithms in the literature. We also prove several lower bounds in this model. A natural question is that given that every graph is kappa plus 1 colorable, and that there are sublinear algorithms for delta plus 1 coloring, can we also get the algorithm that uses kappa plus 1 colors, not just kappa times 1 plus epsilon colors. We answered this question in the negative, and we show that in the streaming and graph query models, any 1 plus kappa plus 1 coloring algorithm would need omega n squared space and omega n squared queries respectively. These results generalize in these models as a kappa plus lambda coloring for some lambda greater than 0 requiring omega n squared over lambda squared space and omega n squared over lambda squared many queries respectively. So in particular, if we want a semi-streaming algorithm, we would need at least kappa plus omega square root kappa colors. A very important thing to note here is that these results hold even if the degeneracy kappa, its value is known to the algorithm in advance. And at the same time, note that our upper bounds make no such assumption. So, and we also prove a combinatorial lower bound for this degeneracy-based coloring. So Asadi et al. Proved a beautiful palette sparsification theorem, which is the main tool for their algorithms. It basically says that if each vertex samples a list of roughly log n colors from a palette of size delta plus 1, then there exists a proper coloring using only the colors from the respective lists. We show that the analogous statement doesn't hold for a palette of size kappa plus 1. And even if we relax the theorem to include more colors in the palette, we cannot get a degeneracy-based coloring in semi-streaming space that uses fewer colors than what we do. Now let me tell you the basic framework that's common to our algorithms. We first randomly colored the graph using L equals to roughly kappa over log n many colors. I'm ignoring some constant and epsilon factors here. After we do this random coloring, we get these monochromatic subgraphs that we call blocks, G1 to GL, and we can prove that the expected degeneracy of each of these blocks gets scaled from the original degeneracy by a factor of 1 over L, that is roughly log n over kappa, and thus the degeneracy of each block is roughly log n. So this is by a Chernoff bound argument. And therefore, the total number of edges in these blocks is roughly n times log n. So this is sublinear in n squared, and now we can fit all these blocks in our memory. Once we collect all the blocks in our memory, we can color each of block Gi with kappa of Gi plus 1 many colors using our favorite offline algorithm. And we use distinct palettes for distinct blocks, which gives proper coloring for the entire graph. The total number of colors we use in this way is log n plus 1 times kappa over log n, because each block has roughly log n degeneracy, and there are kappa over log n many blocks. So the color bound we get is kappa times 1 plus small o of 1. Now this is the basic framework that we use in all our algorithms. And now we just need to carefully implement this framework in each of the models. Consider, for example, the simple insertion-only streaming model. We would randomly color the graph in the pre-processing step. Then, during stream processing, we would collect only the monochromatic edges. Therefore, we collect the monochromatic subgraphs, that is these blocks G1 to GL, which would take up n log n space by this edge bound. And therefore, we can do this in semi-string space. And in the post-processing step, we simply recolor these blocks using the respective Gi plus 1, kappa of Gi plus 1 coloring algorithm, and attain this kappa times 1 plus epsilon color bound on the entire graph. Now, one issue with this framework is that we are saying that we color with kappa over log n many colors, but kappa is not known to the algorithm in priori. So this is a challenge that we need to tackle. And there is also another challenge, particularly in the streaming model, that edge deletions might occur, which would create some issues. So given these challenges, we prove a general theorem, which we call the LDP theorem. LDP stands for low degeneracy partition. And this is our main technical tool. So we have a guess D for the degeneracy K, a sparsity parameter S, which is roughly n log n, and we randomly color the graph with L equals to 2nk over S many colors, which will be roughly k over log n. And this would give us, as before, the blocks G1 to GL. Then the LDP theorem says that with high probability, if our guess is good, that is between the actual value of kappa and double of that, then we have a degeneracy bound of roughly kappa over L with some slack lambda. The block size would be bounded by 2n over L, and the total number of monochromatic edges would be bounded by the sparsity parameter S. For the implementations, let's first consider the streaming model. There lie several challenges here. So since we can have both edge insertions and deletions, the intermediate graphs can become huge, but the final graph might end up respecting the sparsity parameter S. So to fix this, we have a sparse recovery linear sketch given by Gilbert and Indyk, which helps us to recover these monochromatic edges in O tilde S space as long as the final graph is S sparse. If our guess K is too small, then the sparsity bound would be violated, but thus the sparse recovery sketch would fail without raising an explicit error. So to circumvent this, we keep an L0 estimation sketch in parallel that counts the number of monochromatic edges and finally checks if our guess K was actually big enough. We can use the L0 estimation sketch by Ken et al. And also if it may happen that our guess is too large, and then as a result we would end up using too many colors. In that case, it's easy to fix. We would make log n many parallel guesses in powers of 2 and then choose the successful coloring that uses the smallest number of colors. By the LDP theorem, for the guess that is between kappa and 2 kappa, we would actually get a good coloring. The implementations in the other models like query and distributed computing models, it's relatively easier to implement because there is no issue of edge deletion, and so just taking care of parallel guesses suffices to get good colorings. I cannot go into the details of the implementations in this talk, but I would be happy to talk offline or maybe online in the Q&A session. Now let me turn to our lower bound techniques. Recall that for the streaming model, our results say that a kappa plus lambda coloring needs omega n squared over lambda squared space. I just talked about the lambda equal to 1 case here, which says that a kappa plus 1 coloring would require omega n squared space. We reduce from communication complexity as is standard to show the streaming lower bounds. And in particular, we reduce from the index n problem, where there are two players, Alice and Bob. Alice holds an n-bit string and Bob holds an index k between 1 to n. Alice sends a single message to Bob, who should now output the kth bit of x. It is known that Alice's message should be at least omega n in size. Here is the deduction idea. So if we have a graph H that is a clique of size n with one single edge UV removed, then its degeneracy is n minus 2. Therefore, a kappa plus 1 coloring algorithm has no choice but to assign the same color to these two vertices U and V. With this idea in mind, here's the gadget graph for index n square. Our construction ensures that the gadget graph contains this substructure, which looks like a clique with two vertices U0, V0, and another two pair U1, V1, such that in the case that the bit xk is 1, we would have U1, V1 absent in the graph, whereas U0, V0 will be present. and in the xk equal to 0 case, it's the other way around. So in the xk equal to 1 case, our graph would look like this click minus 1 structure, and thus u1, v1 will be assigned the same color by a kappa plus 1 coloring algorithm. And in the xk equal to 0 case, it would assign the same color to u0 and v0. Therefore, just by outputting the I such that ui, vi have been assigned the same color, we solve the index n squared problem, and this gives our corresponding lower bound. Turning to the query model, we reduce from the following unique find problem. So here the oracle has a string ax of size n, and the promise is that it's a unit vector in the sense that there is a single special index I star where the bit is 1 and all other bits are 0. We can query the individual bits of x to the oracle, and making as few queries as possible, we want to output this special index I star. It is known that the unique find problem requires omega n many queries. Here's the deduction from this problem to our coloring problem. So we encode the strings, n squared length strings, into graphs of vertex size n. And so the set of n squared bit strings would be encoded into a class of graphs 8, which has the following property. The graph encoding of the ijth unit vector will have a substructure of the form a click with two corresponding vertices vi and vj missing an edge. So once again we leverage the click minus 1 edge structure, and therefore we can simulate the query algorithm like this, that given a kappa plus 1 coloring algorithm, we emulate a graph oracle ourselves. When the algorithm queries a pair vi vj, we query the oracle the corresponding ijth bit and send the algorithm the encoding of the of xij, which means that we send the corresponding encoding that respects the graph encoding of x. So basically we are feeding the graph that is encoded by x to this algorithm A, which would now output a kappa plus 1 coloring and would assign the same color to vi and vj. Thus, outputting the ij such that vi vj have been assigned the same color solves this unique find problem, and we get our query lower bound. In conclusion, we initiated the study of degeneracy-based coloring in several sublinear models, and we show that it is kind of a better parameter than arboricity, as it gives sharper color bounds and tighter analysis. We gave several color efficient algorithms in different models, and this significantly improves upon the number of colors that have been used by prior algorithms, and especially for real world graphs, this is a large improvement. And we showed a sharp gap between the complexities of delta plus 1 and kappa plus 1 colorings. Recall that delta plus 1 coloring admits a sublinear algorithm, and in fact it can be done in semi-streaming space. On the contrary, even coloring using kappa plus constant many colors has no sublinear algorithm, and for semi-streaming we need at least kappa plus square root kappa many colors. We also showed that sophisticated techniques like palette sparsification cannot beat our color bound by direct implementation. So now I would like to end with some open problems. A very natural open problem is whether we can close this gap between our upper and lower bounds. To recall, we show that a 1 pass semi-streaming algorithm requires kappa plus square root kappa many colors at least, and our upper bound achieves a color bound of kappa plus kappa over log n. We also ask the natural question that if we can improve the upper bound in the multi-pass streaming setting. If we want to improve it all the way to, let's say, kappa plus 1, how many passes do we need? And the last question is kind of open-ended, which asks that our main technical tool LTP, what other applications can it have for graph problems? With that, I'd like to end. Thank you for listening.